The other type of energy change that we saw as we were looking at that heating curve of our ice heating up to become vapor eventually is that we had, in addition to just the heating, which we looked at in the last video, one example of that with the ice, we could repeat that process for the liquid as well. I'll just point that out. But we also saw that that wasn't the only energy that went into the system. A lot of the energy that went in was just to get the ice into a different phase, to go from solid to a liquid or liquid to gas. And so we can also talk about how do we quantify the heat associated with those phase changes. So here it's similar to what we did in the last video but a little bit different. So one thing is that there's no delta T, right? At a phase change, the temperature is fixed. It's at a particular temperature. And that's going to be determined by the substance that you're looking at. And so for ice, for water, right, the 0 degrees Celsius is the temperature at which solid water becomes liquid, and then 100 degrees Celsius when liquid boils and becomes gas. But for other substances, right, they have very different melting and boiling points at those temperatures. So we don't have a delta T associated with this, but what we need to know is what is the energy change for the phase change. And so similar to the idea of a heat capacity, we can keep track of energy associated with phase changes by what we call enthalpies of phase changes. So delta H, and in particular we'll get two types of phase changes, right? Enthalpy of fusion, which is what we call the, I don't know why we use the word fusion for this, but so this is solid to liquid, this is melting. But this is the terminology we use. If you see enthalpy of fusion, it means melting. And enthalpy of vaporization, which is going from liquid to gas at whatever, right, so evaporation or vaporization. Okay, so these are values that are specific to substances, just like the heat capacity. So you'd have to look these up. Some enthalpies of fusion or vaporization that are really common. We're going to look at water a lot. Water matters a lot. So let me see. Where is the? All right. So the molar enthalpy of fusion for water, for H2O specifically, we can look up these values. This is 6.01 kilojoules per mole. And these are usually given as molar enthalpies, meaning that similar to the idea of molar heat capacity, this is how much energy does it take to melt 1 mole of water, or how much energy does it take to boil 1 mole of water. So for H2O, the enthalpy of fusion for 1 mole is equal to 6.01, and for vaporization is a lot more. It's 40.67 kilojoules per mole. So it takes a lot more energy to boil water than just to melt it, to melt ice. So let's go back to our example and see how do we use these. So if we want to calculate Q for the phase change, it's almost the same. It's similar, but we don't have that delta T component. We'll need to know the number of moles. So N here is number of moles. And we need to multiply it by delta H of whichever phase transition. I'll put TRS for transition. So that could be fusion, it could be vaporization. One thing to remember and to be aware of is that, in this case we're thinking about things being heated up. So these enthalpies, these are all endothermic, these will be positive. You can also think about doing the opposite. You could take a gas and condense it, or liquid and freeze it. Those are going to be exothermic processes, and you just change the sign on the enthalpy of fusion or vaporization to get the enthalpies for those. So just one thing I'll mention. So if you're going the opposite direction, if you go gas to liquid, for example, the enthalpy associated with that, delta H, will be the negative of delta H vaporization. So you should have a negative value if it's an exothermic process like this. But that's it. So our phase change, or the heat or energy associated with that phase change, is just number of moles times the enthalpy for that phase transition. So if we have our 15.0 moles of ice that we had before, We can look at the Q for melting it at 0 degrees Celsius. Will just be our 15 moles times our enthalpy of fusion, 6.01 kilojoules per mole. Again, our units cancel here. When we multiply these together, we get 90.2 kilojoules. So that's how much energy it would take to melt the 270 grams of ice. We could repeat this for the vaporization for boiling it, but it's still the same equation here. Okay, so with those examples, we're going to look at more of this in class, and so hopefully this will help you get started on the idea of how do we calculate energy going into or out of the system based on phase changes and temperature changes.